Hello, can you hear me? Uh, I'm, my name is Alexander Mitin, and I'm a VM. What's that? And I'm a VM team lead at Instantiations. Nice to meet you here in Europe. At Instantiations, we continue to invest into our own custom VM, and we are pushing forward its performance. And today I'll tell you about our new JIT compilation engine we are about to introduce in our next 9.2 release. And but let me talk a little bit of what's our new VM, which we use since version 9.0, what it is. So our VM built has a core components built with aid of LLVM. It is compiler infrastructure. It is really powerful and customizable, and it allows us to inject our steps, our passes in order to have the code which we need for our VM, our interpreter, and now it's for JIT. We use a CMake-based build system since the very beginning of our new VM, after we begin to develop our new VM. And it is highly customizable, it is very flexible, it allows us to build various custom versions of the VM. For example, we can just remove all the layer of the LLVM and use pure C implementation of interpreter. We sometimes need it. And as a bonus, all our developers are free to use whatever IDE they want, just to follow code guidelines, and that's okay. Platform functions is our what we call foreign function interface, implemented with aids of libffi. It allows us to implement a full-blown foreign function interface, including synchronous callbacks, asynchronous callbacks, and just directly calls. It is lightweight, and it is written in assembly with the bootstrap code written in C. So it's very lightweight. And we even did some contribution to it. It was a little bit, so we encountered an issue. Well, nobody's perfect. And it was eventually accepted and went into the main development stream of the libffi. As part of our VM, of our VA Smalltalk products, we offer a true headless VM. It has no dependency to UI components. No, it does not execute any UI code. And it is really, really small. For those who was at the presentation of Mariana Martin spec, you could see that the headless VM is only 750 kilobytes, and that's it. Okay, so of course we support the UI, full UI running on the small devices like Raspberry Pi, and the VA Smalltalk product is fully compatible and it is ready for doing IT things. Like I'm referring back to Mariana Martin's spec presentation, which we could see. So he demonstrated lots of stuff like that. And for the new release, we are updating to our VM components. It is a new interpreter for ARM targets. It is LLVM powered, as we do for x86 targets. And additionally, we improved interpreter for x86. Actually, the code is shared between the platforms. There are only a few parts which are really platform specific. And yeah, that's it. So all the changes which we did for ARM automatically go to x86, except with a small exception of if there is a very, very platform-specific parts which require the special handling. Next update is to our foreign function interface, which we call platform function. I already mentioned it. It is returning structs by value. It's not widely used, but sometimes it's really needed, and we do not want to hit the wall and do not know what to do, creating wrappers or whatever. And now it is fully supported. And the major feature which we are about to introduce is our new JIT compilation engine. Currently, it supports only x86, both 32-bit and 64-bit. But it is in progress of implementing ARM targets for JIT. It is not actually ready, but it will be there. So about our new JIT compiler. We developed it in a collaboration with our customer. It is ITAS GmbH company. It is a local German company. We probably know about it. It is a division of Bosch. And during our work at JIT Engine, we did some research and development, and we've tried various ways to how to implement JIT Engine. And besides of that, during all of that research and development work, we tried LLVM to utilize it as a full JIT engine, and we achieved some results, some good results. The performance is just excellent, but there is a big trade-off, and the compilation time is not good enough. We did some improvements to LLVM to building process, and we wasn't be able to achieve any significant results which we can accept. So, and additionally, the footprint of the LLVM library is huge, and it is not really acceptable to use it in IoT tasks, in IoT capable VM, because it is big. So we managed to reduce the size of the binaries until 50 megabytes, but it is not enough. So we will not go into pay that trade-off, and we have chosen another type of the another way of implementing just-in-time compilation. It is template-based JIT. So it is powered by LLVM. So LLVM produces the code for the templates. Template is a portion of code which is capable to substitute any certain byte code and form a natively compiled method. So the compilation is really fast. The performance is really good. I will demonstrate some benchmarks later. So what are the templates? Those templates generated at build time only. They never get into runtime. I mean, compilation of those templates. It never gets to runtime. It's builds on the build time, right? So it contains minimum platform-specific parts. All of the platform-specific things are done by a compiler itself, JIT Compiler, and it contains maximum code reuse with the interpreter. So if we made an improvement into the interpreter, and it will eventually, probably most of the time, it will go to the templates. Okay, if we've got that templates, how to keep them to easy of use, and their LLVM Again, it is our lovely framework. It is capable to store it into the object file, providing all the necessary information we need to build performant native method. So let's see how a typical template looks like. So it is assembly code which handles the pushing of the method literal into VM stack. So notice the symbol in bold, we call it relocation as it comes from object file. Object files are all platform specific, so we use a core format for Windows and ELF for Linux. And there is a little bit of magic compiler does for JIT Compiler does for that symbol. So I'll refer to it later. So compiling process is, it looks really simple. So do copy templates, do some allocation fix-ups. Fix-ups means that the compiler substitutes the symbol which is in bold with the real value, which it knows about what bytecode it currently handling, knows lots of information from the Smalltalk method, and it substitutes this symbol with the real value, and that's it. But it does not look so simple. It is not so simple as it looks like. Besides of just copying templates and applying the real values to the templates, we apply some optimizations to the method which we are about to build. So optimizations are super instructions. It is most commonly used bytecode sequence, and sometimes it's worth to substitute all that sequence with the most optimized template, as it's in use most often. But of course, if there is a jump target into that in the middle of that sequence, then it is not applicable. And since we cannot do all of the we do not know how what bytecode permutation we will have at the Smalltalk method. We can find most commonly used sequences, but it's worth to do something more which can be more widely used. So we trying to avoid stack usage. I mean VM stack, since VA Smalltalk VM is stack VM, and it passes values by stack. So if there is a sequential push-pop operations, no matter what they do, no matter what they perform as the bytecode handlers, there is a way to provide special versions of the templates which use machine register to pass the value. And this helps us to avoid several memory operations, which is good, and it gives us a 10% performance increase in average, and in the best cases, it is 15%. And the third optimization which we did is the inline caches. It is the must for the languages like Smalltalk, and we did it. So you probably know what inline caches are. It's monomorphic inline cache, which transform into a single jump to the target method. And if it fails, then it becomes polymorphic when it goes through several. We did 4 slots. It goes through several slots, checking for the given class. And if it even fails, then it becomes megamorphic. It's much like ordinary sending while lookup. Let's see how a send template looks like. Notice two symbols in bold. The first one is return address. We need to know where we should return from method invocation. And the second is for compiler to perform a big magic behind that. So the compilation process is not only copying templates. During that process, the compiler gathers all the necessary information to perform, to substitute, again, at the call site, which we see here, we never know what object comes to, correct? And this information which compiler gathered during method traversing, Smalltalk method traversing, it gathers information of what object could be there to perform various, for example, various lookup procedures. For example, it could be determined that the method which is about to invoke belongs only to this class and no need to traverse the entire hierarchy, and it's substituted there. And at the end, this symbol, send argc22, eventually becomes monomorphic send site. It's just a jump, so it will be substituted with a jump value, jump target value, and it goes jump. Note that inline cache data is here. It is not actually a part of the templates. Compiler sets it up here for the purposes of morphing caches into from polymorphic to megamorphic and from monomorphic to polymorphic. Okay, that's it. And a couple of words about the compilation process. Since the results speed of the compiling is really fast, we the compilation process looks really simple. We just flash a code cache and traverse every stack frame. Not actually every, but we traverse only the frames marked as if it is running native code. So we change the program counter. It's a jump target for native methods. We change it back to the Smalltalk counterpart. And since we're just traversing it, we do not do any additional memory, we do not apply additional memory footprint. So it's really quick and really, really, really nice. Okay, let's see some benchmarks. The benchmarks we used are mostly taken from benchmark game project. We ported to VA Smalltalk. And for simplicity, all of the diagrams will have value which less is better. And colors which are darker is JIT. Light colors is interpreter mode, and we compared it with our older VM from our release release 8. So integer arithmetics looks pretty good, and notes that even interpreter outperforms our old VM. Fraction arithmetic also looks good. And Factorial. Factorial is an interesting part because you can see that interpreter outperforms JIT. Sometimes it happens, and we have the capabilities to determine which methods are not worth to execute, but it is done at the Smalltalk compiling time and during packaging. So some methods are marked with a flag, which means that we should not ever try to natively compile that method. Sometimes it becomes wrong, as we can see, and we probably need to add some improvements. So our JIT compilation engine should also figure out if it's still worth to compile that method. Okay, next is prime summing. Looks pretty good. Calculations of p number digits. Looks good. Generating of image of Mandelbrot. Looks nice. Not so outperformant, but still nice. Spectral normalization. Looks good. Binary trees, creating of lots of binary trees, traversing them, deallocating, inserting, deleting, whatever. Looks nice. And body, calculations of orbit of the planets. For full description of the benchmarks, what they do, please refer to that game benchmarks projects. You can easily find it on internet. FASTA, it's calculating of DNA chains. Looks even nice. And Caminus Redux. This is very, very loose, a little bit. It sometimes happens. But this looks really nice as well. And this is my favorite part. It is our customers' feedback who access early customer access program. So they did some testing, and they have 17.5 seconds for the ordinary task at the old VM, and 12.8 for new one, which use JIT, new JIT. That's nice. So conclusion, our new VA Smalltalk release 9.2 is currently available on the early customer access program, ECAP, at instantiations.com/ECAP. And the release is upcoming in a few weeks. We're still testing. So contacts, can you see them? So thank you for your attention. Questions, anyone? Okay.
For the factorial, there are tons of different algorithms in Smalltalk. Iterative, recursive. Which one did you use here?
It's recursive.
Okay, then I understand.
Sure. More questions?
Well, you said that after pasting all the templates one after the other, you do some sort of optimization to avoid to push pops pairs, and you said that then you pass the values through the register, right?
Right.
So how you do that? Do you have some sort of register allocation algorithm on top of that, or something similar?
This actually came a little bit automatically because we use a little VM and we have a free register which is not in use. And we pinned this register to a special VM register. So we just simply, and we know that it is free at that time, so we could use it. We could just use it.
Okay, so you have only one register to pass, this fast way. So
right.
If you have like 2 arguments, then you can only pass one argument through the register and not the other. Or
this bytecode sequence is rare, and not often we can encounter it. We did some statistic analysis for what bytecodes currently in use, what bytecode sequences in use. So this rarely happens. So it's not worth to implement.
Okay.
Hello. You mentioned that some of the methods are tagged not to be JITted.
Right.
So can you tell us a bit more?
It's a Smalltalk compiler does this job. It detects some. It maintains the. Let me figure it out how to describe it. So the Smalltalk compiler detects the length of the method, the bytecodes they use, and it looks for it not to exceed some threshold. So if it exceeded, then it marked as not compiled, to do not compile. Nothing else.
Okay. And do you take into account if this is a megamorphic or things like that, or this is just purely static from the method code?
Sorry, could you please repeat?
I said, do you only take the source code of the method, or do you take if this is a highly polymorphic method?
No, it's just it's performed and compiled some of the Smalltalk method into bytecodes, not into the native code, which I mentioned that we should implement that facility at the JIT compiler itself. It is not, it's still on plans, but the performance looks really good currently. More questions? Okay, thank you very much.